Hello everyone, my name is Namrata Verma, Assistant Professor in the Electronics and Telecommunication Department at Sri Santosh Rungta Group of Institution, Rungta College of Engineering and Technology, Bhilai, Chhattisgarh. In the previous lecture, we already discussed about amplitude modulation, its generation and description, in which we already discussed the definition of amplitude modulation, its mathematical representation, modulation index, advantages, disadvantages, application and generation of amplitude modulation. Today, we are going to discuss the topic of amplitude modulation, its representation and frequency spectrum. In today's lecture, we are going to discuss the topic with the following points. We will start with the representation of amplitude modulation, then the bandwidth of amplitude modulation, power calculation of amplitude modulation, efficiency of amplitude modulation, double sideband suppressed carrier amplitude modulation, which is also called as DSB-SC, and methods of generating double sideband suppressed carrier. Basically, there are two methods of generation of DSB-SC. The first one is balanced modulator and the second one is ring modulator. Now, first we will see the representation of amplitude modulation. The amplitude modulation is used in electronic communication, mostly used for transmitting information via a radio carrier wave. Amplitude modulation works by varying the strength or amplitude of the carrier wave in proportion to the information being sent while keeping the frequency and phase of the carrier signal constant. The expression of amplitude modulated signal is given by S of t, which is equal to the AC plus xt whole multiplied by cos omega ct, where xt represents the modulating signal, which is given by am cos omega mt, and omega ct is a high frequency sinusoidal signal that itself does not convey any useful information. The message signal x of t is the actual signal that contains the information which needs to be transmitted, and it has typically low frequency as compared to the carrier signal frequency. This figure represents the message signal in the time domain and in the frequency domain. From the frequency domain figure, we can observe that the frequency of message signal xt is band limited with omega m. That means no frequency higher than the frequency omega m. Now, the carrier signal. Carrier signal is a high frequency signal which is given by AC cos of omega ct, where AC represents the amplitude of carrier wave which is constant and omega c represents the angular carrier frequency. It is represented by the following figure in the time domain and in the frequency domain. From the time domain, we can observe that the carrier frequency has constant amplitude, and from the frequency domain, we can observe that the carrier frequency has constant frequency. The presence of message signal xt in the amplitude modulation adjusts this amplitude to encode the message. The equation 1 shows that the carrier amplitude is adjusted by the instantaneous value of the message signal xt. Then from the equation 1, we can write S of t is equal to AC plus am cos omega mt whole is multiplied by cos omega ct, which can be also written as S of t is equal to AC cos omega ct plus am cos omega mt into cos omega ct. Now, we are applying the trigonometric formula in the second term, and then after applying that, we can write it as S of t, that is equal to AC cos omega ct plus am by 2 cos omega c plus omega mt plus am by 2 cos omega c minus omega mt, which can be also written as S of t, that is equal to AC cos 2 pi fct plus am by 2 cos 2 pi into Fc plus Fmt plus am by 2 cos 2 pi into Fc minus Fmt. The frequency form the above expression, we can say that the amplitude modulated signal consists of three main components. The first component is the carrier frequency having frequency Fc. The second one is the upper sideband having frequency Fc plus Fm, and the third one is the lower sideband having frequency Fc minus Fm. The figure C represents the amplitude modulated signal. The first one represents the time domain representation of amplitude modulated signal, and the second one represents the frequency domain representation of amplitude modulated signal. From the frequency domain representation, we can observe that we have two sideband. First one is the upper sideband with frequency omega c plus omega m, and the second one is the lower sideband with frequency omega c minus omega m. Now, next we are going to cover the bandwidth of AM wave. The bandwidth of amplitude modulation determines the range of frequency that the signal occupies and the impact the selection of channel spacing and transmitter or receiver design. Bandwidth calculation is essential for avoiding interference with other signal and optimizing the use of available spectrum. Now, the definition of bandwidth. Bandwidth refers to the width of a range of frequencies within which a signal is transmitted or received. The bandwidth represents the difference between the upper frequency and the lower frequency in a continuous band of frequency. The band of the AM wave can be calculated as difference between the upper frequency and the lower frequency. The amplitude modulated signal is given by St is equal to AC cos 2 pi Fct plus AM cos 2 pi Fc plus Fmt plus AM by 2 cos 2 pi Fc minus Fmt. From the above equation, we have the upper frequency, that is Fc plus Fm, and the lower frequency is Fc minus Fm. Therefore, the bandwidth of AM wave will be the difference between the upper frequency, which is Fc plus Fm, and the lower frequency, which is Fc minus Fm. Therefore, the bandwidth is the difference between the D's upper frequency and the lower frequency, and after the simplification we will get the bandwidth is twice of Fm for the amplitude modulation. Now, let us consider one example to understand this bandwidth. If an AM radio station uses a carrier frequency of 1 megahertz and the highest frequency in the audio signal is Fm, which is equal to 5 kilohertz, then the bandwidth required for the AM broadcast would be, according to the formula, bandwidth is equal to twice of Fm. Here Fm is equal to 5 kilohertz, therefore bandwidth will be 10 kilohertz. Let us see the practical implication of bandwidth. The bandwidth requirement of the highest frequency component of the message signal is essential for the following factors. The first one is channel spacing, which determines how far apart different channel frequency must be to avoid interference, which is crucial for frequency allocation. And the second one is the filter design. The AM receiver uses the bandpass filter, which is centered on the carrier frequency with the bandwidth sufficient to pass the entire AM signal while blocking out the signal from the adjacent channel. And the third one is transmission quality. The bandwidth affects the quality and clarity of the received signal. Insufficient bandwidth can lead to the loss of information and increased distortion. Now, we will see the power calculation of AM wave. The equation of amplitude modulated wave is represented by St is equal to AC cos 2 pi Fct plus AM by 2 cos 2 pi Fc plus Fmt plus AM by 2 cos 2 pi Fc minus Fmt. In terms of modulation index mu, the above equation is represented as St is equal to AC cos 2 pi fct plus AC into mu by 2 into cos 2 pi fc plus fmt plus AC into mu by 2 into cos 2 pi fc minus fmt. Give it equation number 2. The power of AM wave is equal to the sum of carrier power, upper sideband power and lower sideband power. So, the total power PT will be summation of these three, which is total power is equal to carrier power PC plus upper sideband power P USB plus lower sideband power P LSB. We know that the standard formula for the power of sinusoidal signal is V RMS square by R, and V RMS is given by Vm by root 2 for the sinusoidal signal. So, it will be Vm by root 2 square divided by R. Now, first let us find the carrier power. From equation 3, the carrier power will be AC by root 2 square by R, where AC represents the maximum amplitude of a carrier signal. So, it will be AC square by 2R. Similarly, upper sideband power will be equal to Vm by root 2 square by R, and the Vm represents the amplitude of USB, and from equation number 2 we have Vm is equal to AC into mu by 2. Therefore, upper sideband power will be equal to P USB, that is equal to AC into mu upon 2 root 2 whole square divided by R, or which will be equal to AC square into mu square divided by 8R. Similarly, the lower sideband power will be the same value as that of the upper sideband power, that is equal to AC square into mu square divided by 8R. Now, add these three powers to get the total power. Therefore, the total power is equal to AC square divided by 2R plus AC square into mu square divided by 8R plus AC square into mu square divided by 8R. Then the total power PT can be also written as AC square upon 2R can be taken as a common. So, PT is equal to AC square upon 2R whole is multiplied by 1 plus mu square by 4 plus mu square by 4, or it can be also written as PT is equal to AC square upon 2R whole is multiplied by 1 plus mu square by 2. Hence, the total power is PT is equal to AC square upon 2R in bracket 1 plus mu square by 2. In terms of carrier power, the total power is PT is equal to, the first term is nothing but the carrier power. So, it can be represented by PC into 1 plus mu square by 2. If the modulation index is equal to 1, then the power of the AM wave is equal to 1.5 times the carrier power. Therefore, the total power will be 3 by 2 times of PC, that is carrier power, or it can be also written as 1.5 times of carrier power. It can be observed that the ratio of total power to the carrier power is PT upon PC, that is equal to 1 plus mu square upon 2. Now, we will see the efficiency of AM wave. The transmission efficiency of AM wave is the ratio of the transmission power which contains the information, that is sideband power, to the total transmitted power, and it is represented by eta. Therefore, the efficiency is eta is equal to upper sideband power, that is represented by P USB, plus lower sideband power, that is represented by P LSB, divided by total power represented by PT. In terms of modulation index mu, it can be written as mu square upon 4 into Pc plus mu square upon 4 into Pc divided by total power, that is 1 plus mu square upon 2 whole is multiplied by Pc, which can be simplified as eta efficiency is equal to mu square upon 2 divided by 1 plus mu square divided by 2, or eta is equal to mu square divided by 2 plus mu square into 100%. Next we will see double sideband suppressed carrier. Transmission of amplitude modulated wave is insufficient because 2/3 of the power is carried by the carrier signal, which contains no information. If the carrier signal is suppressed and only the sideband remains, then we can save up to 2/3 of the power. This type of suppression does not affect the information signal, and then the resulting signal obtained by suppression of carrier signal is called double sideband suppressed carrier system, which is also called as DSB-SC system. Let us consider the same mathematical expression for modulating signal and the carrier signal as we have considered earlier. The modulating signal is represented by x of t, that is equal to am cos omega mt, where am represents the maximum amplitude of the modulating signal and omega m represents the maximum angular frequency, which can be also written as x of t, that is equal to am cos 2 pi fmt, where fm represents the frequency in hertz, and the carrier signal is represented by Ct, that is equal to AC cos of omega Ct, where AC represents the maximum amplitude of the carrier signal and omega c represents the angular frequency of carrier signal, which can be also written as Ct is equal to AC plus cos 2 pi fct, where fc represents the frequency of the carrier signal in hertz. Mathematically, we can represent the equation of DSB-SC wave as the product of modulating signal and the carrier signal. Therefore, the DSB-SC wave can be represented as S of t, that is equal to xt into Ct. Now, substituting the value of x of t and Ct, and then the above equation will be S of t, that is equal to am cos 2 pi fmt into AC cos 2 pi fct. Now, applying the trigonometric formula of cos A into cos B, then the above equation will be St is equal to am into AC by 2 cos 2 pi fc plus fmt plus am into AC by 2 cos 2 pi fc minus fmt. From the above equation, we can observe that it has only two sidebands, upper sideband with frequency fc plus fm and the lower sideband with frequency fc minus fm. Figure D represents the frequency spectrum of double sideband suppressed carrier wave, which indicates it has only two sidebands and the carrier is suppressed. The bandwidth is defined as the difference between the upper frequency and the lower frequency. Hence, the double sideband suppressed carrier modulated signal has the two frequencies. So, the maximum and the minimum frequencies are fc plus fm and fc minus fm respectively. Therefore, the bandwidth of double sideband suppressed carrier will be fc plus fm minus fc minus fm, or the bandwidth will be twice of fm. Thus, the bandwidth of double sideband suppressed wave is same as that of the AM wave, and that is equal to the twice of frequency of the modulating signal. Now, we will calculate the power of DSB-SC wave. The power of DSB-SC wave is equal to the sum of power of upper sideband and the lower sideband frequency component. Therefore, the total power PT is equal to P USB plus P LSB. And we know that the standard formula for the power of cos signal is V RMS square divided by R. And the RMS value of cos signal is Vm upon root 2, where Vm is maximum amplitude of cos signal. And therefore, power of cos signal is P, that is equal to Vm upon root 2 whole square divided by R. Now, let us find the power of upper sideband and lower sideband one by one. From the equation of DSB-SC, amplitude of upper sideband is AM into AC divided by 2. Therefore, upper sideband power is P USB, that is equal to AM into AC divided by 2 root 2 whole square, whole is divided by R, or which can be also written as P USB is equal to AM square into AC square divided by 8R. Similarly, we will get the lower sideband power, which is same as that of the upper sideband power, which is P LSB, that is equal to AM square into AC square divided by 8R. Now, we will add these two sideband powers to get the total power of DSB-SC wave. Therefore, total DSB-SC power is PT, that is equal to summation of P USB plus P LSB, or PT is equal to, substituting the value of P LSB and P USB, then we will get PT is equal to AM square into AC square divided by 8R. Therefore, the power required for transmitting DSB-SC wave is equal to the power of both the sidebands. The advantage of DSB-SC modulation is that it consumes low power as obtained by other modulation due to suppressed carrier in this modulation. And the disadvantages of DSB-SC modulation is its complex detection as a wave modulation due to the carrier being suppressed, which has its product proportional to the message signal. Now, next we will see the generation of DSB-SC signal. There are two types of generator which will generate DSB-SC signal. The first one is balanced modulator and second one is ring modulator. The balanced modulator consists of identical AM modulator, two identical AM modulator. These two modulators are arranged in balanced configuration in order to suppress the carrier signal. Hence, it is called as balanced modulator. The block diagram of balanced modulator is shown in the figure. This figure consists of two amplitude modulator. The modulating signal MT is applied as input at upper amplitude modulator, and 180-degree phase shift modulating signal, that is minus of MT, is applied at the input of lower amplitude modulator. Another input at both the amplitude modulator are output from the local oscillator, which will generate the carrier signal AC cos 2 pi FCT with amplitude AC and frequency FC. Then the output of upper amplitude modulator is represented by S1T, and it is given by S1T is equal to AC into 1 plus Ka cos omega mt, which is multiplied by cos omega Ct, and the output of lower AM modulator is represented by S2T, and it is given by S2T is equal to AC into 1 minus Ka cos omega mt, which is multiplied by cos omega Ct. Thus, the summer block produces an output S of t, which is the difference of S1T and S2T. Therefore, the output of summer block will be St, which is equal to S1T minus S2T, and after simplification we will get St is equal to 2 AC Ka cos omega mt into cos omega Ct. By comparing the output of summer block with the standard equation of DSP-SC wave, we will get the scaling factor of 2 Ka, where Ka is nothing but the constant. So, we can say that here at the output we will get the double sideband suppressed carrier. The second method for generating the DSP-SC is ring modulator. The block diagram of ring modulator is shown in the figure below. In this ring modulator circuit, the 4 diodes are connected in the form of ring, in which all 4 diode points are in the same manner. All the 4 diodes in the ring are controlled by a square wave carrier signal of frequency Fc, which is applied through the center tapped transformer. For positive half cycle of the carrier signal, the diode D1 and D3 are on and the diode D2 and D4 are off. In this case, the message signal is multiplied by +1. For negative half cycle of the carrier signal, the diode D2 and D4 are on and the diode D1 and diode D3 are off. In this case, the message signal is multiplied by -1. This results in 180-degree phase shift in the resulting DSP-SC wave. From the above analysis, we can say that the 4 diode D1, D2, D3 and D4 are controlled by the carrier signal. If the carrier signal is a square wave, then the Fourier series representation of carrier signal is given by Ct is equal to 4 upon pi summation n is equal to 1 to infinity minus of 1 to the power n minus 1 divided by 2n minus 1 whole is multiplied by cos 2 pi Fct into 2n minus 1. We will get the DSP-SC wave S of t, which is just the product of this carrier signal Ct and the message signal m of t. Then the DSP-SC wave will be the S of t, that is equal to 4 upon pi into summation n is equal to 1 to infinity minus 1 to the power n minus 1 divided by 2n minus 1 into cos 2 pi Fct into 2n minus 1 whole is multiplied by mt, where mt is the message modulating signal. The above equation represents the DSP-SC wave which is obtained at the output of the transformer of ring modulator. This DSP-SC modulator are also called as the product modulator, as they produce the output which is the product of the 2 input signal. Thank you.